In this lecture, we'll discuss inodes and hard links. Each file on disk has a data structure called index node or inode associated with it, which is fixed in length. This structure stores metadata information about the file, such as the type, file's permission, file's owner and group, timestamp information, file size, and so on. You can see most of the information stored in a file's inode in the output of ls-l. The inode structure contains all file information except the file contents and the name. Each inode is uniquely identified by an integer number called inode number. To see it, run ls with the -i option. You can combine it with other options as well. Yes, you heard me right. The file name and the file contents are not part of the inode. In the inode structure, there are only some pointers to the data blocks where the file contents are saved. But where's the file name if it's not in the file's inode structure? A file name is an entry in a directory. Basically, directories are two-column tables where the first column is the file name and the second column is the inode number. Something like this. This is a column and this is another. This is a simplified approach, but I think it's a good one for you to understand. I'm creating a new file using the touch command. When I refer to a file, like say cat a.txt, it will search in the current directory for the corresponding inode number of a.txt, for this number. Having that number, the kernel can identify the file and all the information about it. So, as a conclusion, the file name doesn't belong to the file structure. It's just a string, and the pointing between the file structure and the file name happens through the data structure of the directory that contains the file name. An association between a file structure and a file name is called hard link. In fact, this is a hard link. In the current directory, a.txt was associated with this number. By the way, that's what this one means. It means one hard link. You can have more associations, and I mean names, to the same file structure on disk. So the same file can be accessed through many names in the same directory or different ones. To see the number of hard links, run ls-l or stat. This regular file has one hard link. You can create a new hard link by running the ln command. ln comes from link. At this moment, the file called a.txt has only one hard link because there's one name that points to the inode structure. To create a new link to the same file structure, I run ln, the existing name, and the new name, like ln a.txt b.txt. So in fact, I've created a new file name for the same file structure. We can see that both files have the same inode number and the number of hard links is now 2. Note that b.txt is not a copy of a.txt. The information on the disk is saved only once and both files point to the same data. If I change one of them, the other will be changed as well. For example, I'm using a redirection I've configured greater than a.txt. I'm changing a.txt. I have redirected the output of the command to the file. The other file name to the same structure has the same contents. It's the same. You can also create a hard link in another directory. For example, ln, the existing file, b.txt, and the new hard link. My backup, c.txt. Now, there are 3 hard links or 3 names to the same file structure on the disk. You see, there are 3 links. And it's the same inode number. If you delete a file using rm, then only the entry from the directory that contains the file is removed and the link count of the inode is decremented. Only when it reaches 0, the disk space associated with the inode and the inode itself is freed for further reuse. I'm removing a.txt. They have the same inode number and the number of hard links is 2. You know that there are 2 hard links for the file to each b.txt points and want to find out the other one. Suppose you don't know that c.txt in my backup is a hard link. To do that, use the find command with the -inum option, like this. Find the current directory, inum, and the inode number. And it found all the links. Also note that you cannot create a hard link to a directory or a hard link to a file on a different partition or disk. A hard link cannot cross the file system boundaries. Let's try to create a hard link to /etc. Hard link not allowed for directory. However, if you run the ls-l command on a directory, like this, you notice a very large number of links. The etc directory has 130 hard links. Maybe you wonder how that's possible. And the answer is that there are 130 names to the same structure, the etc directory. One is etc, another reference is the dot which belongs to each directory, and its reference to itself, this one. This is the second link. And then there are 128 subdirectories, and each of them contains the double dot, which is a reference to its parent, so in this case, to etc. If I take any directory from /etc, for example this one, and I run ls -lia, and the directory, you'll notice there the double dot, this one. This is in fact etc. So, another hard link. This is its inode number, which is equal to the inode number of /etc. It's the same number. One useful application of the hard links is to allow files, programs, and scripts to be easily accessed in different directories without making copies of the same file. And if you want to find files by the number of hard links, use the find command with the -links option. Let's find all the files in /usr with more than one link. Find /usr -typef -links +1. All these files have more than one link. Let's add the -ls option. 5 hard links, 10 hard links, 3, and so on. The number is always greater than 1. Besides hard links, there's another type of link called soft link, symbolic link, or symlink. We'll take a short break, and in the next lecture, we'll discuss symlinks.